Okay, so this question's got quite a lot of marks and it actually contains quite a lot of key ideas when it comes to connected particles. We start by observing a few things, and the first thing is thinking about how the particles will begin to move. Well, because P is heavier, then we can see that it must start to move or accelerate in this way. That's important to note, and we are going to focus on P. Always the case with connected particles. Just focus on one particle at a time. And what do we know? Well, we know that the weight is 0.5 g newtons and that the tension is always going away from the particle. And importantly, that the acceleration, as far as P is concerned, is going downwards. And using F equals ma, therefore, we know that since it's accelerating downwards, the resultant force is 0.5 g minus the tension, because the 0.5 g is the greater force as it's accelerating downwards. And so that is our F in F equals ma, and the mass is obviously 0.5, and A we don't know. And so here we have our equation of motion for P. Now let's focus on Q. The weight is 0.4 g newtons, the tension again is away from the particle, and this time it is accelerating upwards. And so T is now the greater force. T minus the weight, this time this is the resultant force, is equal to the mass times the acceleration. And so we have the equation of motion for Q, and this was the equation of motion for P. And so we can solve. Now from here, it's simple to work out the acceleration first. Simply by adding the equations together, we can eliminate T, and then solving for A is equal to g over 9, and that we can just substitute in, implies that T is equal to 4g over 9. Okay, now from here, we are going to look at the subsequent motion of Q, because the string breaks. Let's consider just before the string breaks, what happens? Well, it has an initial speed of u before it started to move or accelerate. It then starts to ascend with a constant acceleration of g over 9, which we found out, and that it has traveled for 0.2 seconds. And in this time, it would have reached a certain velocity, we don't know, and ascended a certain height. And so we have two unknowns, but we have enough information to work out V and to work out S. So just using those two equations, we can solve for V and S, and we have the following values. Now for the motion of the particle after the string breaks, it is very important to note that it will then be falling freely under gravity. So that's the crucial part. And there's one more very important fact. So let's just clear it up and imagine that it's just a particle that's been projected upwards. What would its initial speed be after the string breaks? Well, that obviously has to be exactly the final speed before the string breaks. And from here, we know that if we take upwards to be positive, then downwards would be negative, and we now consider the particle to be falling freely under gravity, and therefore the acceleration will be minus g, acting downwards. It ascends up to a certain height, greatest height above ground, and then falls down towards the ground. And we're going to say this, when the string breaks, is our zero displacement level. And from there, we know that it would have descended a total distance of s plus 2 meters. But we know s. And therefore, using s equals ut plus half at squared, we can solve for t, which makes t to be 0.66. Now, supposing I took downwards to be positive, what would happen there? Well, quite simply, that if downwards was positive, let's remind ourselves that the moment the string broke, it was moving upwards. So upwards will be negative. Acceleration downwards is now positive, will become positive g. And its displacement would now be a positive quantity. And if we worked this out, of course, as expected, we still get exactly the same value for t. Using s equals ut plus half at squared, we end up with exactly the same outcome. And finally, I'd like to draw our attention back to our zero displacement and connect what we've just found to our understanding of pure mathematics, and in particular coordinate geometry. So let's again focus on the zero displacement. This time I'm going to draw a horizontal axis and a vertical axis, and I'm going to label those T and S. Now we know that S equals ut plus half at squared, and we found the value of u and a, so let's substitute those in. And as we can see, S is simply a function of t, and because it's a negative quadratic, supposing we were to plot the points, it would look something like that, and the distance below the point where the string breaks corresponds exactly to this point on the graph. If you like, usually the y coordinate, and the time corresponds to the corresponding x coordinate. And as we know from quadratic functions that by the symmetry there is a second solution, a second point on the curve where it is exactly the same distance from the horizontal axis. But here we reject this solution because in the context of mechanics we do not have a negative time, so we understand that we must reject that solution. And this is also known as a displacement time graph. So I hope you can see the nice connection between pure mathematics and applied mathematics from this question. Thank you very much for watching.